Explanation. A group is a set G together with a binary operation star that combines any two elements to produce a third element of the same set. The operation must satisfy four simple rules, called group axioms. Closure for any a B in G, the result a star B is also in G. Associativity. For any a B, C in G, the product of a star B then C equals a star the product of B star C. Identity element. There exists an element E in G such that E star A equals a star E equals a for every A in G. Inverse element. For each A in G there is an element A inverse in G with a star A inverse equals A inverse star A equals E. Illustrative example 1, the set of integers z with addition plus. Adding any two integers stays an integer closure. Addition is associative, 0 acts as identity, and each integer n has an inverse negative and hence z plus is a group. Illustrative example 2, the set of non-zero real numbers r times with multiplication dot. Multiplying two non-zero reals never gives 0, closure. The operation is associative, the identity is 1, and the inverse of x is 1 over x. Thus r times with multiplication dot is a group. Illustrative example 3, non-group, the natural numbers n under subtraction. Subtraction can leave the set, for example 3 minus 5 equals negative 2 not in n, so closure fails and there is no identity that works for all elements. Hence this is not a group. Groups can be sorted in several useful ways. Finite versus infinite. A group is finite if it contains a limited number of elements, otherwise it is infinite. For example, the cyclic group Z5 equals the set 0, 1, 2, 3, 4 under addition modulo 5 is finite, size 5. The group Z plus is infinite because there are infinitely many integers. Abelian versus non-abelian. A group is abelian, meaning commutative, when the order of operation does not matter. A times B equals B times A for all A comma B. Most everyday examples are abelian, such as Z plus or the addition of vectors in the plane. A classic non-abelian group is the set of 2 by 2 invertible matrices under multiplication, denoted GL sub 2 of R. Take A equals the matrix with row 1 0, 1, row 2 1 0, and B equals the matrix with row 1 1 1, row 2 0 1. Then a B is not equal to B. Another well-known non-abelian group is the symmetry group of a triangle, denoted D3 or S3. Rotations and flips do not commute. Summarizing. Finite abelian, Z sub n, direct products like Z sub 2 times Z sub 3. Finite non-abelian, dihedral groups D sub n for n greater than or equal to 3, permutation groups S sub n for n greater than or equal to 3. Infinite abelian, Z plus R plus, additive group of rational numbers Q plus. Infinite non-abelian, GL sub n of R for n greater than or equal to 2, the group of all bijections of an infinite set, the infinite symmetric group. Explanation: A subgroup H of a group, G is a subset of G that itself forms a group under the same operation. To check whether a subset is a subgroup, we usually apply the subgroup test : a non-empty subset H is a subset of G is a subgroup if and only if for all in B and H the element A times B inverse, or equivalently A times B and A inverse, also lies in H. Why the test works: closure under times and inverses together guarantee all four group axioms inside H. The identity automatically appears because taking A equal to B gives A times A inverse equals E in H. Example 1: in the integers under addition, the even integers 2z equal open brace ... minus 4, minus 2 0 2 4 ... close brace form a subgroup. For any two evens 2m, 2n, 2m minus 2n equals 2 open parenthesis m minus n close parenthesis is still even, satisfying the test. Example 2: in the multiplicative group of real numbers non-zero under multiplication, the set open brace 1, minus 1 close brace is a subgroup. Both are their own inverses and the product of any two is again plus or minus 1. Basic properties: the intersection of any collection of subgroups of G is again a subgroup, possibly empty. But if the collection includes at least one subgroup, the intersection contains the identity. The union of subgroups is not generally a subgroup, unless one subgroup is contained in the other. Every group G has at least two trivial subgroups: the set containing E, the trivial subgroup, and G itself, the impermanent subgroup. Lagrange's theorem states, In a finite group G, the order, meaning the number of elements of any subgroup H, divides the order of G symbolically. The order of G equals the index of H in G times the order of H, where the index of H in G is the number of distinct left cosets of H in G. Proof sketch: consider the left cosets GH, which are the set of G times H such that H is in H. For each element G in G, any two cosets are either identical or disjoint. Every coset has the same size as H because multiplying by a fixed G gives a one-to-one correspondence from H to G. H, the distinct cosets together partition G. So the order of G equals the number of cosets multiplied by the order of H, therefore the order of H divides the order of G. The order of any element in G, which is the smallest positive integer m such that a to the m equals the identity, divides the order of G, because the cyclic subgroup generated by A has order equal to the element's order. A group of prime order P has no proper non-trivial subgroups. Its only subgroups are the trivial subgroup containing only the identity and the whole group itself. If the order of G is n and D divides n, there may exist a subgroup of size D. Cauchy's theorem guarantees a subgroup of prime order dividing n. But the existence of a subgroup for an arbitrary divisor is not assured unless extra conditions hold. For example, in cyclic groups, a subgroup of every divisor always exists. In the cyclic group Z12, which has size 12, the subset containing 0, 4, and 8 forms a subgroup of order 3, and indeed 3 divides 12. A cyclic group is a group that can be generated by repeatedly applying the group operation to a single element. Formally, G is cyclic if there exists G in G such that G equals the set of G to the K, where K is in Z. The element G is called a generator. The set 0, 1, 2, up to n-1 with addition modulo n denoted plus sub n is a finite cyclic group of order n. The element 1 generates the whole set because k times 1 is congruent to k modulo n, producing every residue class. In fact, any k with greatest common divisor of k and n equals 1 is also a generator. These are the units modulo. The integers under ordinary addition form an infinite cyclic group. The element 1 or negative 1 generates all integers. Negative 2 equals negative 1 plus negative 1, negative 1, 0, 1, 2 equals 1 plus 1, Examples: Z sub 6 equals the set 0, 1, 2, 3, 4, 5. Generators are 1 and 5 because greatest common divisor of 1 and 6 equals greatest common divisor of 5 and 6 equals 1. Z sub 8 has generators 1, 3, 5, 7. In the multiplicative group containing 1 and negative 1, order 2, negative 1 is a generator because negative 1 squared equals 1. Cyclic groups are especially simple. Every subgroup of a cyclic group is again cyclic, and the subgroups of Z sub n correspond exactly to the divisors of n for each divisor D divides n. The set 0 D 2D n minus D is a subgroup of order n over D. The order of an element in a group G is the smallest positive integer m such that a to the m equals the identity E. If no such m exists, the element is said to have infinite order. In Zn under addition, the order of bracket k bracket, the residue class of k, is n divided by the greatest common divisor of k and n. For example, in Z12, the element bracket 8 bracket has order 12 divided by the greatest common divisor of 8 and 12, which equals 12 divided by 4 equals 3, because 8 plus 8 plus 8 is congruent to 0 modulo 12. In the multiplicative group of non-zero real numbers, the element -1 has order 2 because negative 1 squared equals 1. Any positive real number other than 1 has infinite order. Relation to group order: by Lagrange's theorem, the order of any element divides the order of the group when the group is finite. Consequently, the possible orders of elements are restricted to the divisors of the group order. Order of subgroups: a subgroup H of a finite group G has order that divides the order of G. Moreover, if H is cyclic, its order equals the order of its generator. For example, in Z20, the subgroup generated by 4 consists of 0, 4, 8, 12, 16, having order 5, which divides 20. Infinite groups: in the additive group of integers, every non-zero element has infinite order because there is no finite m such that m times 1 equals 0. In contrast, the element 0 has order 1 because 0 equals the identity. Understanding orders helps in many tasks: finding generators, determining possible subgroup sizes, and solving equations like a to the k equals b within the group. Two groups G and H are isomorphic, written G isomorphic to H, if there is a bijective function phi from G to H that respects the operation. Phi of a star GB equals phi of a star H phi of B for all n and B in G. For cyclic groups, the classification is especially clean. Criterion: any two cyclic groups of the same order are isomorphic. Moreover, there is exactly one infinite cyclic group up to isomorphism. Proof sketch. Let G equal angle bracket G angle bracket be cyclic of finite order n. Define phi from Zn to G by phi of bracket K bracket equals G to the K. This map is well defined, bijective. Every element of G appears as G to the K for a unique K modulo n, and respects addition. Phi of bracket K plus L bracket equals G to the K plus L equals G to the K times G to the L equals phi of bracket K bracket times phi of bracket L bracket. Hence phi is an isomorphism. For infinite cyclic groups, G equals angle bracket G angle bracket with no positive integer m such that G to the m equals the identity. Define phi from Z to G by phi of K equals G to the K. The same reasoning shows phi is an isomorphism. Thus uniqueness up to isomorphism. All finite cyclic groups of size n are essentially the same structure as Zn. All infinite cyclic groups are the same as Z. Example: Z4 and the group of fourth roots of unity brace 1, I, negative 1, negative I brace under multiplication are isomorphic via phi of bracket K bracket equals I to the K. The additive group of even integers 2Z is isomorphic to Z via phi of K equals 2K. Isomorphisms preserve all group theoretic properties: order of elements, subgroup lattice, abelianness, etc. When solving problems, you can often replace a complicated cyclic group by the familiar Z, N, or Z after proving they are isomorphic. Explanation: below are typical exam-style questions together with concise model solutions. Question 1. Show that the set S equals 0, 2, 4, 6 with addition modulo 8 is a group. Identify its identity and inverses. Solution: verify the axioms. Closure: adding any two even numbers modulo 8 yields an even residue, for example 4 plus 6 equals 10 equivalent to 2. Associativity: inherited from integer addition. Identity: 0 because 0 plus a modulo 8 equals a for all in S. Inverses: for each element a find B with a plus B modulo 8 equals 0. 0 inverse equals 0, 2 inverse equals 6 since 2 plus 6 equals 8 equivalent to 0, 4 inverse equals 4, 6 inverse equals 2. Hence S is a group. Question 2. List all subgroups of Z12. Solution: subgroups correspond to divisors of 12. Divisors 1, 2, 3, 4, 6, 12. Order 1, the set containing 0. Order 2, the set 0 and 6 generated by 6. Order 3, the set 0, 4, 8 generated by 4. Order 4, the set 0, 3, 6, 9 generated by 3. Order 6, the set 0, 2, 4, 6, 8, 10 generated by 2. Order 12, Z12 itself. Question 3. In the group D, 4 symmetries of a square, what is the order of the rotation R by 90 degrees? Use Lagrange's theorem to justify. Solution: applying the rotation 4 times returns the square to its original position, so R to the 4th equals the identity and no smaller positive power does. Hence the order of R is 4. Since the order of D4 equals 8, Lagrange's theorem tells us the order of any element must divide 8. 4 indeed divides 8. Question 4. Prove that every subgroup of a cyclic group is cyclic. Solution: let G equal the generated by G and H is a subgroup of G. If H equals the set containing the identity, it is cyclic. Otherwise, let H be the element of smallest positive exponent such that G to the H is in H. Show that every element of H can be written as G to the H raised to K. Thus H equals the subgroup generated by G to the H. Question 5. Determine whether Z15 units, the units modulo 15, is cyclic. If it is, exhibit a generator. Solution: Z15 units equals the set 1, 2, 4, 7, 8, 11, 13, 14, order 8. Compute powers of 2 modulo 15. 2, 4, 8, 1 gives order 4. Try 7. 7 to the first equals 7. 7 squared equals 4. 7 cubed equals 13. 7 to the 4th equals 1, order 4. Try 11, 11 to the first equals 11, 11 squared equals 1, order 2. Try 13, 13 to the first equals 13, 13 squared equals 4, 13 cubed equals 7, 13 to the fourth equals 1, order 4. No element has order 8, so the group is not cyclic. It is isomorphic to Z4 cross Z2.